Carbon monoxide is a poisonous gas that is formed in automobile engines and released in their exhaust. When a car idles in an enclosed area, such as a garage, the concentration of carbon monoxide can quickly become dangerous or even lethal. Carbon monoxide reacts with molecular oxygen present in the air of the garage and produces a far less toxic gas, carbon dioxide. From an energy standpoint, carbon dioxide is greatly favored in this reaction, and given enough time, essentially all of the carbon monoxide reacts with oxygen and is converted into carbon dioxide. This might lead you to think that carbon monoxide should not present a health risk, since there is plentiful oxygen in the air to react with the carbon monoxide. However, this is not the case. In spite of the fact that the carbon monoxide is eventually converted to carbon dioxide, the rate of the reaction is so slow that the carbon monoxide concentration in the garage can quickly build to a toxic level. When the exhaust of the car is run through a catalytic converter, however, the reaction rate is much faster, and most of the carbon monoxide quickly reacts with oxygen and is converted into carbon dioxide. The reasons carbon monoxide and oxygen react so slowly with each other, the role of the catalytic converter in speeding up the reaction, and other topics relating to reaction rates are covered in this program. Before introducing reaction rates, it is important to understand what a rate is. A rate is defined as the amount of change per unit time. A rate that you are probably familiar with is rate of travel, or speed. Suppose you are in a plane that travels from London to New York in 6 hours, and the distance from London to New York is 5,585 kilometers. You can easily set up an equation that gives you the rate of travel. Simply divide the distance traveled, or change in position, in this case, 5,585 kilometers, by the time, which is 6 hours. In this example, the rate is 931 kilometers per hour. In contrast, a sailboat on a calm day travels at a much lower rate, perhaps only 8 kilometers per hour. Speed is only one example of a rate. Here are two more rates. At a ski resort, you might be able to rent a snowboard at the rate of $25 per day. The number of vibrations a guitar string makes per second determines the note produced by the guitar. Notice that in each of the three rate examples, the unit of time is different. The time unit for the airplane's speed is hours. The snowboard rental is days. And the vibration of the guitar string is measured in seconds. The unit of time selected for a specific rate is usually based on convenience. For example, it is easier to comprehend that a car is moving at a rate of 60 kilometers per hour, which is 37 miles an hour, than the equivalent speed in seconds, which is 0.017 kilometers per second, or 0.010 miles per second. Since many chemistry and physics problems involve a conversion in the time unit, it is important to understand how to convert units of time. It is fairly simple to make these conversions. Say you want to know how many kilometers the plane in the previous scenes travels in 1 second. In this case, set up the equation by multiplying the speed, 931 kilometers per hour, by the conversion factors. 1 hour equals 60 minutes, and 1 minute equals 60 seconds. Remember to cancel units. Arriving at the correct units in your final answer is a sign that you are doing things correctly. Performing the calculation shows the plane travels 0.259 kilometers per second. Since you are now familiar with rates, we can move on to discuss the rates of chemical reactions. Chemical reactions can be extremely fast, as when a balloon full of hydrogen gas quickly reacts with oxygen and bursts into flame in the presence of a spark. Reactions can be much slower as well. The reactions that converted compressed plant matter into coal took many thousands of years. The careful study of reaction rates, including the factors that influence them and the mechanisms by which they occur, is known as kinetics. Understanding the kinetics of a reaction can help chemists devise methods for speeding up important industrial processes, such as petroleum refining, which produces gasoline and oil. A detailed understanding of reaction rates also gives chemists a picture of what is going on at the atomic level during chemical reactions. The following scenes follow the progress of the decomposition or breakdown of the colorless gas dinitrogen pentoxide to show how the rates of chemical reactions are measured. If a sample of dinitrogen pentoxide gas is placed in a sealed container, it decomposes, or breaks down, into brown nitrogen dioxide gas and molecular oxygen. The balanced equation for this reaction is shown on your screen. This reaction does not occur instantaneously, so at a given time only a certain fraction of the dinitrogen pentoxide has decomposed. For example, suppose that 0.050 moles of the reactant are placed in a previously empty 1-liter container. The initial concentration of dinitrogen pentoxide is 0.050 moles per liter. Square brackets around a chemical formula indicate concentration. The dinitrogen pentoxide immediately starts decomposing, so there are less molecules of the reactant in the same volume. This means there is a lower concentration of the reactant after a given time. A sample taken after 1 minute reveals that the concentration of dinitrogen pentoxide has gone down to 0.033 moles per liter. What has happened to the concentrations of nitrogen dioxide and oxygen? Since the decomposition of the reactant leads to the formation of the products, the concentrations of these two gases increase. In the last scene, you saw the change in concentration of dinitrogen pentoxide over a 1-minute period. Although the data were given in terms of the concentration of dinitrogen pentoxide, this did not have to be the compound that was actually measured. Often, it is easiest to measure the concentration of one particular reactant or product during the course of a reaction, but this may not necessarily be the substance one is studying. For example, in the reaction from the last scene, it is relatively easy to measure the concentration of nitrogen dioxide, which is a brown gas, by using a device that determines the concentration of the gas by how brown it becomes. Even when you are investigating the breakdown of dinitrogen pentoxide, it may be easier to measure the concentration of nitrogen dioxide and use the measurement obtained to calculate the concentration of dinitrogen pentoxide. In the previous scene, it was noted that as the concentration of dinitrogen pentoxide decreases, the concentrations of nitrogen dioxide and oxygen increase. If you know the change in concentration of one reactant or product, you can determine the changes in concentrations of all the others based on the stoichiometric relationships of the balanced equation. In this reaction, the balanced equation shows every 2 moles of dinitrogen pentoxide that breaks down produces 4 moles of nitrogen dioxide and 1 mole of molecular oxygen. For an example of how to calculate changes in concentration from stoichiometric relationships, look at the following data for the production of nitrogen dioxide. The initial concentration of nitrogen dioxide in the 1-liter container was 0 moles per liter, and after 1 minute the concentration of nitrogen dioxide was 0.034 moles per liter. Since the concentration of nitrogen dioxide is 0.034 moles per liter, and the volume of the container is 1 liter, there is a total of 0.034 moles of nitrogen dioxide. The experimental data that you have are for nitrogen dioxide, but the compound under investigation is dinitrogen pentoxide. How many moles of dinitrogen pentoxide must have decomposed to produce 0.034 moles of nitrogen dioxide? As you can see from the balanced equation, for every 2 moles of dinitrogen pentoxide broken down, there are 4 moles of nitrogen dioxide created. Multiplying 0.034 moles of nitrogen dioxide times the conversion factor of 2 moles of dinitrogen pentoxide for every 4 moles of nitrogen dioxide shows that 0.017 moles of reactant decomposed. Now that you can determine the concentration of all the reactants and products, you can learn to calculate reaction rate. The reaction rate of a given product or reactant is the change in the concentration of that reactant or product per unit of time. In mathematical terms, the reaction rate for a given reactant or product equals the change in its concentration divided by the change in time. Change in concentration is equal to the concentration of a reactant or product at time 2, which is the time the second measurement is made, minus its concentration at time 1, the time the first measurement is made. The change in time is simply time 2 minus time 1. The uppercase Greek letter delta is used to signify change, so the equation can be rewritten as delta concentration divided by delta time. The concentration of reactants becomes smaller as they are used up to form products, so the concentration of reactants at time 2 will be smaller than the concentration at time 1. This means that for reactants, the overall expression for the reaction rate will be negative. Since it is conventional to report reaction rates as positive numbers, simply multiply the value found for reactants by -1. When finding the reaction rate for products, the negative sign is not necessary, since products are being formed and the concentration at time 2 will be greater than at time 1. It is also important to clearly note the product or reactant for which you are determining the rate, since the rate of formation or disappearance depends on the stoichiometric ratio in the balanced equation. For example, hydrogen will be consumed twice as fast as oxygen in the reaction 2H2 plus O2 yields 2H2O, because the ratio is 2 moles of hydrogen per mole of oxygen. In the last scene, you learned how to determine the rate at which a specific reactant or product reacts. You also learned that the reaction rate for different products or reactants differs based on their stoichiometric coefficients. To determine the overall rate for the entire reaction, simply divide the rate of each of the reactants and products by its stoichiometric coefficient. Doing this normalizes the reaction. In other words, it gives you only one reaction rate for the overall reaction. As an example, consider the reaction of nitrogen and hydrogen gases, which produces ammonia gas. The reaction rate for a given reactant, say hydrogen, is the change of its concentration divided by time and multiplied by -1, since hydrogen is a reactant. To get the overall reaction rate, divide the rate by its stoichiometric coefficient, which for hydrogen is 3. If you had measured the reaction rate of ammonia, what would you do to find the overall rate? Do you see why you divide by 2, which is the stoichiometric coefficient? In this case, you do not multiply by -1, since ammonia is a product and the rate is already positive. The normalized rates equal each other, and normalizing gives you one reaction rate for the entire reaction, so you don't have separate rates for each reactant and product. In the next scene, you will see a numerical example of how to determine the reaction rate of a specific reactant, and how to use stoichiometric coefficients to obtain the overall reaction rate. Using the equation from the last scene, you can calculate the average reaction rate of dinitrogen pentoxide in the first minute of the experiment shown in previous scenes. Substitute the known values into the rate equation shown on the screen. Subtracting the concentration at time 1, 0.050 moles per liter, from the concentration at time 2, 0.033 moles per liter, gives a difference of negative 0.017 moles per liter. This is divided by the change in time, which is time 2, 60 seconds, minus time 1, 0 seconds. This means the change in time equals 60 seconds. The change in the concentration of the reactant, dinitrogen pentoxide, over the first minute of the reaction is negative 2.8 times 10 to the negative fourth moles per liter second. Since a reaction rate cannot be negative, multiply by negative 1, which gives you a reaction rate of 2.8 times 10 to the negative fourth moles per liter second. Many reaction rates are given in moles per liter second, but slower reactions may be given in terms of minutes, hours, or even days. To normalize the reaction, divide 2.8 times 10 to the negative fourth moles per liter second by the stoichiometric coefficient of dinitrogen pentoxide, which is 2. This gives an overall reaction rate of 1.4 times 10 to the negative fourth moles per liter second. Earlier, you saw that when 0.017 moles of dinitrogen pentoxide decomposed in the first minute, 0.034 moles of nitrogen dioxide were created. Using this data to solve for the reaction rate of nitrogen dioxide gives the value 5.7 times 10 to the negative fourth moles per liter second. Note that in this case, you do not multiply by negative 1, since nitrogen dioxide is a product. Dividing 5.7 times 10 to the negative fourth moles per liter second by the coefficient of nitrogen dioxide, which is 4, yields an overall reaction rate of 1.4 times 10 to the negative fourth moles per liter second. This is the same value obtained earlier when the rate of decomposition of dinitrogen pentoxide was normalized, which is the reason for normalizing the reaction. Now assume the reaction discussed in the previous scene continues, and measurements are made at 1-minute intervals. The chart shown on your screen shows the concentrations of dinitrogen pentoxide at the first 3 time intervals. Do you notice anything about the differences in concentration? The size of the difference in concentration gets smaller each minute, meaning that less dinitrogen pentoxide is breaking down, and therefore the reaction rate is decreasing. For example, in the first minute, 0.017 moles of dinitrogen pentoxide decompose. In the second minute, 0.011 moles decompose. And in the third minute, only 0.007 moles decompose. From the last scene, you know that the rate at which dinitrogen pentoxide decomposes over the first minute is 2.8 times 10 to the negative fourth moles per liter second. Substituting values from the chart in the rate equation shows that the average rate of dinitrogen pentoxide decomposition over the second minute is 1.8 times 10 to the negative fourth moles per liter second, and over the third minute, it is 1.2 times 10 to the negative fourth moles per liter second. In other words, as the concentration of dinitrogen pentoxide decreases, the reaction goes slower. The data from the last scene, along with further measurements, have been plotted on this graph. Time is measured along the horizontal or x-axis. and the concentration of the reactant is measured along the vertical, or y-axis. In the previous scenes, the average reaction rates were determined for 3 one-minute periods. However, these are average rates, and the rate at any given instant in one of these periods, known as the instantaneous rate, is not likely to be the same as the average rate. While this program will not go into the math involved in determining the instantaneous rate, it is important to realize that the instantaneous rate at a given time is related to the slope of the line that is tangent to the curve at the time the rate is measured. The tangent line for a point on the curve is the line that touches the curve at only that point. The slope of a line is equal to rise over run, or the distance the line travels along the y-axis divided by the distance it travels along the x-axis. As a reaction proceeds, the rate of reaction decreases, so the slope of the tangent line becomes flatter. Just as a skier will go slower if she starts at a less steep part of the hill, the rate of reaction is slower in less steep portions of the curve. The reaction rates given in the remainder of the program will be instantaneous rates. The rates of chemical reactions depend on several factors, some of which may already be familiar. You may have noticed that food cooks faster at a higher temperature, or that it is easier to start a fire by lighting twigs and other small pieces of wood than it is to light a large branch. Among the factors that influence reaction rate are the concentration of the reactants, the temperature at which a reaction is conducted, the surface area of solid or liquid reactants, the presence of catalysts, and the nature of the reactants. Each of these factors will be addressed in the next section of the program. The nature, meaning the identity and state of the reactants themselves, affects reaction rates. At one extreme, alkali metals, such as metallic potassium, will react quickly when exposed to air, water, and many other substances. At the other extreme, a noble gas such as argon does not react under normal circumstances. Another important factor is the physical state of the reactants. In general, a substance in the gas phase reacts faster than that substance in the liquid phase, which reacts faster than that substance in the solid phase. This is because particles in the gas phase move more freely than particles in the liquid phase, and particles in a liquid move more freely than particles in a solid. Particles that move more freely are able to collide more often, and as you will see later in the program, more collisions lead to a faster reaction rate. Almost all reactions are slower at lower temperatures and faster at higher temperatures. For many chemical reactions, the reaction rate doubles for every 10 degrees Celsius rise in temperature, though this is a crude approximation. An example of a reaction that takes place faster at higher temperatures is the hardening of glue. This means you have less time to work with the glue at higher temperatures before it hardens. Another example of the effect of temperature on reaction rates is the activity level of insects. Insects do not maintain a constant internal temperature. Since the temperature inside the insect is essentially the same as the outside temperature, the reactions occurring inside the insect occur more slowly at lower temperatures, and the insect tends to move more slowly. This is why you can accurately estimate the temperature by counting the number of times a cricket chirps in 1 minute. Since the activity of the cricket decreases at lower temperatures, it chirps at a lower rate when it is cold. At the beginning of the program, you learned that carbon monoxide from car exhaust reacts slowly with atmospheric oxygen. Inside a car's catalytic converter, the temperature and concentration of reactants are similar to the rest of the exhaust system. Yet the reaction takes place much more quickly in the catalytic converter. This is because in the catalytic converter, metals, such as platinum and palladium, act as catalysts. A catalyst is a substance that increases the rate of a reaction and is not chemically changed at the end of the reaction. Since a catalyst is unchanged by a reaction, it can continue to facilitate the conversion of reactants into products. This allows a small amount of a catalyst to catalyze a large number of reactions. Hydrogen peroxide decomposes very slowly into water and oxygen at room temperature, but if a small amount of manganese dioxide is added, the reaction will occur quite rapidly. When the reaction has run its course, all of the manganese dioxide can be recovered. A large variety of catalysts affect many different reactions. Living organisms possess a class of catalysts called enzymes, which are large molecules that increase the rate of biologically important reactions. A granule of sugar can sit unchanged on a table for a long period of time without reacting with oxygen. However, if an ant eats it, the sugar will rapidly react in the presence of oxygen, producing carbon dioxide and water and providing energy to the ant. The breakdown of sugar in the ant is catalyzed by a series of enzymes that increases the overall reaction rate, even at room temperature. The enzymes are the same at the end of each reaction as they were at the start, and are therefore available to catalyze the breakdown of more sugar molecules. Another factor that increases reaction rate is increasing the surface area of a solid or liquid reactant. This is why, as mentioned earlier, it is easier to light small pieces of wood than it is to light one large piece that has the same mass. Each time a large object is broken up into smaller pieces, the surface area increases. For example, a cube with the volume 8 cubic centimeters has a surface area of 24 square centimeters. If it is cut 3 times to make 8 cubes, each with a volume of 1 cubic centimeter, the total volume is still 8 cubic centimeters, but the surface area increases to 48 square centimeters. The same effect means the fine spray of gasoline from the fuel injector of a car has a greater surface area than a large stream of gasoline, so the fine spray reacts more quickly with oxygen. A dramatic example of the effect of surface area can be seen in this demonstration using the spores of the Lycopodium plant. Spores in a pile are hard to ignite, but as you can see from the video, when the surface area of the spores is increased by blowing on them, they ignite readily. You have already seen that dinitrogen pentoxide decomposes more quickly at higher concentrations. In general, the higher the concentration of reactants, the faster the reaction rate. The following demonstration illustrates the relationship between changes in concentration and the number of potential reactions. Each pool table on your screen is the same size, so the table on the left with 15 balls on it has a higher concentration of balls than the one on the right, which has 2 balls. A cue ball shot at random is much more likely to hit a ball on the table having a higher concentration of balls than it is on the table having a lower concentration of balls. This is analogous to varying the concentration of reactants. A higher concentration can lead to more reactions. As you have just seen, increasing the concentration of reactants increases the reaction rate. The demonstration with the pool tables showed that there are more collisions occurring among molecules at higher concentration. But does every collision lead to a reaction? The answer for the majority of reactions is no. In a typical sample of gas at standard temperature and pressure, a single oxygen molecule makes over 1 billion collisions per second. If all collisions led to reactions, then reactions between gases would be nearly instantaneous. However, You have seen that many of these reactions are quite slow. Clearly, the mere fact that two gas molecules collide is not sufficient to cause them to react. A theory known as collision theory distinguishes between effective collisions, which lead to reactions, and ineffective collisions, which do not. The two factors determining the effectiveness of a collision are the energy of the colliding particles and the orientation of the particles when they collide. These factors will be explored in the next few scenes. For a collision to be effective, the colliding particles must have enough kinetic energy. Kinetic energy is the energy related to motion. The more kinetic energy a particle possesses, the faster it travels. To understand why the kinetic energy of the reactants is important, consider the reaction in which two molecules of hydrogen iodide react and form one molecule of hydrogen and one molecule of iodine. In order for these reactants to be converted into products, the bond between the hydrogen atom and the iodine atom in each hydrogen iodide molecule must first be broken. It requires a certain amount of energy to break the bond between hydrogen and iodine, and that energy comes from the collision of the reactant molecules. Only molecules that collide with sufficient energy are capable of breaking bonds. Notice that when these two toy cars collide at low speed, the driver stays in place. But when they collide at high speed, the driver flies out. In this demonstration, the ejection of the driver is analogous to the breaking of a chemical bond, because sufficient energy is required for either event to occur. In the last scene, you learned that only collisions of particles with sufficient kinetic energy have the ability to produce a reaction. Raising the temperature of a sample of gas increases the average kinetic energy of the molecules in the sample. This explains why reaction rates increase at higher temperatures. Not all of the molecules in a sample have the same kinetic energy. For a given sample of molecules, there is a distribution of kinetic energies, which means that only a fraction of the molecules will have sufficient kinetic energy to react. The graph on the screen shows the fraction of molecules in a sample plotted against their kinetic energies at a given temperature. Notice that as you move to the right on the graph, kinetic energy increases, so the molecules in this portion of the graph have greater kinetic energy. Observe what happens when the temperature increases by 10 degrees. The curve flattens out and shifts to the right. This means that at a higher temperature, more molecules have high kinetic energy. You can see this when the two curves are superimposed. The colored portions under the curves show the fraction of molecules that have at least a given kinetic energy. Do you see why the percentage of high-energy molecules is greater at higher temperatures? In addition to kinetic energy, molecules also have potential energy. Potential energy is stored energy. Within molecules, energy is stored in chemical bonds. This graph portrays the energy change that occurs during the course of a reaction. The horizontal axis of the graph represents the course of the reaction over time, and the vertical axis represents potential energy. The reaction shown is exothermic, meaning it releases energy. In an exothermic reaction, the reactants have higher potential energy than the products. If little energy is required to break chemical bonds in the reactant molecules prior to forming the products, the graph is drawn like this, with only a slight hump in the curve. However, in most cases, substantial energy is needed to break bonds among reactants during the reaction process, and a larger hump is created. This hump represents the extra amount of energy required to make the reaction occur, which is referred to as the activation energy of the reaction. Bonds are being broken and reformed during the course of the reaction. which results in potential energy increasing until it reaches a peak, which is the activation energy. When molecules collide with sufficient kinetic energy, existing bonds can be broken, allowing the formation of new bonds. Each reaction has a characteristic activation energy, and higher activation energies act to make reaction rates slower, as you will see in the next scene. In this demonstration, the marbles on the table represent the molecules taking part in an exothermic reaction. When marbles are on the table, they represent the reactants at a high potential energy. When they are on the floor, they represent the products at a lower potential energy. Shaking the table gives the marbles energy, and this represents the kinetic energy imparted to the particles in a system by raising the temperature. At first, there is no lip around the table, a situation analogous to a reaction with no activation energy. Notice that with even a little bit of energy, marbles fall onto the floor. The marbles that fall off the table onto the floor represent molecules that have been converted to products. Now a medium-sized lip is placed around the edge of the table, representing a low activation energy. The table must be shaken harder for any marbles to fall off. Lastly, a tall lip is placed around the table, representing a high activation energy. At a low or medium degree of shaking, corresponding to a low or moderate temperature, no marbles fall off. Even with energetic shaking, only a small fraction of the marbles has enough energy to make it over the lip and leave the table. The situation is similar for molecules in a reaction. If the activation energy is high, as it is when the lip around the table is high, only a few of the reactants have enough energy to get over the hump and react. Since only a few of the reactants have the energy to make it over the hump, corresponding to activation energy in a given time, it is analogous to having a slower reaction rate. Just as you would have to gently shake the table for a long time to get all of the marbles to fall on the floor, it takes a long time for reactants to be converted to products at a low temperature. Putting your understanding of activation energy together with the concept of kinetic energy distribution allows you to understand how increasing the temperature of most reactions increases their rates. Here is a kinetic energy distribution at 298 kelvins, or 25 degrees Celsius. This vertical line represents the activation energy, or the minimum energy necessary for the reaction to occur. Notice that only a small fraction of the molecules, shaded in blue, has enough energy to react. Now, look at the distribution of kinetic energy at 308 kelvins. The activation energy necessary for the reaction stays the same, so at the higher temperature, a larger fraction of molecules equals or exceeds the activation energy. This portion is shaded in red. Logically, if a higher fraction of molecules at a higher temperature has enough energy to react, the proportion of collisions that can lead to reactions will be higher, and the reaction rate will increase. This is why many reactions, such as the hardening of glue, occur faster at a higher temperature. Not all collisions with sufficient kinetic energy result in reactions. The way in which the molecules strike each other is also important in bringing about a reaction. Think about a batter in a baseball game. The rapid movement of the bat and the ball are analogous to two particles meeting with enough kinetic energy to react. When the bat contacts the ball can go in a number of directions. It can go straight down or straight up, to the left, or to the right, depending on how the bat strikes it. If the bat strikes the ball in just the right way and with sufficient energy, the batter hits a home run. When molecules strike each other with the correct orientation, they form what is called an activated complex. This is an extremely unstable, short-lived structure in which bonds are in the process of breaking and reforming, and which quickly breaks apart. During the period of time in which the activated complex exists, it is referred to as being in the transition state, which corresponds to the highest potential energy. Just as it takes a certain bat speed and orientation to produce a home run, it also takes enough kinetic energy and the correct molecular orientation to form an activated complex. Earlier in the program, you learned that a catalyst is a substance that increases the rate of a reaction, but is unchanged at the end of the reaction. Catalyzing a reaction is similar to driving a car home versus walking home. You will end up in the same place, but driving the car will get you there faster. In an earlier scene, you saw how manganese dioxide catalyzed the breakdown of hydrogen peroxide into oxygen and water. The final amounts of products and reactants will be the same, whether the decomposition of hydrogen peroxide is catalyzed or uncatalyzed, but the catalyzed reaction occurs much more rapidly. A catalyst works by providing a new pathway for the reaction, lowering the activation energy. If the activation energy is viewed as a wall that the reactants must have enough energy to get over, a catalyst can be viewed as knocking off the top of the wall. This means that a greater fraction of reactant molecules at a given temperature has enough kinetic energy to react, and the reaction rate will be higher. As you can see in the accompanying graphs, lower activation energy means that the fraction of molecules with energy sufficient to react will be greater. Because catalysts act by lowering the activation energy of a reaction, they can only increase the rate of a reaction, but they cannot cause a reaction to occur that will not happen under the reaction conditions. Earlier in the program, you saw that the rate at which dinitrogen pentoxide decomposes to form nitrogen dioxide and water is related to its concentration. At a high concentration, dinitrogen pentoxide breaks apart at a faster rate. As you learned earlier, most reactions proceed faster when the concentration of the reactants is higher. Chemists have determined that for the majority of reactions, the reaction rate is proportional to each reactant's concentration raised to an experimentally derived power and multiplied together. The power to which each concentration is raised can be fractional, negative, 0, or a positive whole number. For ease of understanding, this program only deals with whole number powers. You cannot determine from the balanced equation for the reaction the power to which a concentration is raised. It can only be determined by experiment. This is an important point to keep in mind. In the last scene, you found out that the reaction rate is proportional to the product of the concentrations of each reactant raised to an experimentally derived exponent. At any given temperature, the proportion can be changed into an equation by multiplying the expression by a constant, symbolized by K. The term K is called the rate constant for the reaction. The rate constant is different for each reaction and changes with temperature. This equation, in which the rate equals K times the concentration of each reactant raised to a power, is called the rate law for the reaction. Knowing a reaction's rate law is valuable to chemists because it allows them to determine how quickly a given product will be produced from known concentrations of reactants. As you will see in the section of the program on reaction mechanisms, the rate law also helps chemists understand what happens on the molecular level during a reaction. If you know the rate law for a reaction, it is possible to use the concentrations of the reactants and the rate of the reaction to determine the value of K the rate constant. In these calculations, the concentrations used are generally those at the beginning of the experiment, called the initial concentrations. Look at the reaction in which nitrogen dioxide and molecular fluorine combine, forming the explosive gas nitrile fluoride. The rate law for this reaction is rate equals K times the concentration of nitrogen dioxide times the concentration of fluorine. The experimentally derived exponent for both nitrogen dioxide and fluorine is 1, and an exponent of 1 is not written. When the initial concentration of both reactants is 0.020 moles per liter, the rate of reaction is 0.016 moles per liter second. Given these data, it is a straightforward procedure to calculate the rate constant. First, substitute the known values into the rate law equation, and then solve for K. Performing the calculation gives you a numerical value of 40. But what are the units? The rate is in moles per liter second, and each concentration is in moles per liter. When the concentrations in the denominator are multiplied, the resulting unit is moles squared per liter squared. When you invert and multiply the units, the result is liter per mole second. So the rate constant for this reaction is 40 liters per mole second. The units of the rate constant can vary, as you will see in the next scene. Here is another example of how to determine a rate constant, this time for the decomposition of dinitrogen pentoxide, a compound studied earlier in the program. At a temperature of 328 kelvins, which is 55 degrees Celsius, the reaction rate for the breakdown of 0.30 moles per liter of dinitrogen pentoxide is 4.5 times 10 to the negative fourth moles per liter second. The rate law for the decomposition of dinitrogen pentoxide is rate equals K times the concentration of dinitrogen pentoxide. Notice that the power to which the concentration is raised, 1, is not the same as the coefficient in the balanced equation, which is 2. It is important to remember that the powers in a rate law expression are not necessarily the same as the coefficients in the balanced equation, but are determined by experiment. To find the value of the rate constant, substitute the known values into the rate law equation. Solving for K and canceling units gives you a value of 1.5 times 10 to the negative third per second. Once you know the value of K, you can use it to determine the rate of decomposition of any concentration of dinitrogen pentoxide at 328 kelvins. Did you notice that the rate constants in the two examples had different units? In the first case, the units are liters per mole second, and in the second case, they are per second. The unit of the rate constant differs depending on what is known as the reaction order. The order of a reaction is equal to the sum of the powers of the concentrations in the rate law expression. For example, the reaction that forms nitrile fluoride is a second-order reaction because the concentration of each reactant is raised to the first power, and 1 plus 1 is 2. The decomposition of dinitrogen pentoxide is first order because its concentration is raised to the first power. Here is the rate law for the reaction of nitric oxide and molecular hydrogen. Do you see why this is a third-order reaction? The individual reactants are described by their individual order as well. The order of a given reactant equals the power to which its concentration is raised. For example, the reaction of nitric oxide and hydrogen is second order with respect to nitric oxide, and first order with respect to hydrogen. Since 1 plus 2 equals 3, The reaction is third order overall. The order of the individual reactants can be determined using experimental data for concentration and rate. For example, look at the data collected for 3 experiments on the breakdown of sulfuryl chloride. For each initial concentration of sulfuryl chloride, the initial rate of decomposition was measured. To determine the order of the reactant, start by writing the general rate law for the reaction, which, in this case, is rate equals K times the concentration of sulfuryl chloride raised to some power, x. To determine the power to which the concentration is raised, observe the relationship between the increase in concentration and the increase in rate. When the initial concentration is doubled, as it is between the first and second experiment, the reaction rate doubles. When the initial concentration is tripled, as it is between the first and third experiment, the reaction rate also triples. Because of the one-to-one relationship between the change in concentration and the change in rate, the reaction is first order in sulfuryl chloride and first order overall. Therefore, the rate law expression is rate equals K times the concentration of sulfuryl chloride to the first power, or just K times the concentration of sulfuryl chloride. Now look at data collected for the decomposition of hydrogen iodide gas into molecular hydrogen and molecular iodine. In this case, when the initial concentration is doubled, as it is between the first and second experiment, the initial reaction rate increases by a factor of 4. Between the first and third experiment, the initial concentration is tripled, and the initial rate increases by a factor of 9. This shows that the reaction rate is proportional to the square of the concentration, since 2 squared is 4, and 3 squared is 9. The rate law, therefore, is rate equals K times the square of the concentration of hydrogen iodide. Can you see that the reaction is second order in hydrogen iodide and second order overall? Now that you know the rate law, you can determine the value of the rate constant by using any set of values for rate and concentration from the chart in the rate law equation. For example, substituting the values at time 1 into the rate law equation gives the equation 8.0 times 10 to the negative 6 moles per liter second equals K times the square of 0.010 moles per liter. Solving for K gives the answer 0.080 liters per mole second. It is also possible to determine the rate law for reactions having more than one reactant. To see how this is done, take a look at the reaction of nitric oxide and molecular oxygen, which produces nitrogen dioxide. To determine the rate law for this reaction, start by writing the general form of the rate law, rate equals K times the concentration of nitric oxide to the unknown power x times the concentration of oxygen to the unknown power y. Now examine the data that were collected for the reaction. When you are presented with data on 2 variables, in this case the concentration of nitric oxide and the concentration of oxygen, compare situations where only one variable changes at a time. For example, in the first 2 experiments, only the concentration of oxygen changes. This allows you to determine the effect of changing the concentration of oxygen. In this case, when the concentration of oxygen is doubled, the rate also doubles. This means that the reaction is first order in oxygen. In the second and third experiments, only the concentration of nitric oxide changes. So you can use this data to determine the effect of changing the concentration of nitric oxide. As you can see, doubling the concentration increases the reaction rate by a factor of 4. which means the reaction is second order in nitric oxide. Thus, the rate law is written as rate equals K times the square of the concentration of nitric oxide times the concentration of oxygen. This reaction is second order in nitric oxide, first order in oxygen. Adding the exponents shows that the reaction is third order overall. You have seen that in order to react, molecules must collide with a certain minimum energy and the proper orientation. Even with the incredibly large number of collisions that occurs among gas molecules every second, the collision of two molecules with the correct orientation and sufficient kinetic energy to react is still relatively infrequent in all but instantaneous reactions. Now look at the balanced equation for the combustion of heptane, which is a component of gasoline. One molecule of heptane reacts with 11 molecules of oxygen and forms 7 molecules of carbon dioxide and 8 molecules of water. If it is so unlikely for two molecules to come together with the correct orientation and energy to react, how is it possible for a heptane molecule to collide effectively with 11 oxygen molecules at the same time? The answer is, it is not. The reaction of heptane with oxygen, as well as many less complicated reactions, goes through a series of steps called a reaction mechanism. While the reaction mechanism for the reaction of heptane and oxygen is far too complex for the scope of this program, the following scenes show reaction mechanisms for several simpler reactions. Each of the steps in a reaction mechanism is known as an elementary process. The elementary processes in the hypothetical reaction mechanism on your screen show the progress of the reaction from reactants to products through intermediate steps, much as this map shows the progress of a passenger flying from San Francisco to Detroit through Dallas. Elementary processes are inferred from experiments and observations, and generally cannot be proven. When all of the elementary processes of a reaction mechanism are added, they produce the overall balanced equation. This is because a substance on one side of an elementary process cancels the same substance on the opposite side of another elementary process. In a similar way, the layover in Dallas is canceled when the legs of the flight are added to give the overall trip from San Francisco to Detroit. An intermediate is a substance thought to be present in some steps of the reaction mechanism, but which is not part of the overall balanced equation. An intermediate disappears by the end of the reaction, so it is canceled when the elementary processes are added. The intermediates in a reaction mechanism are believed to exist for such a short time that they are usually undetectable, although some have been detected. Here is the proposed reaction mechanism for the decomposition of nitrile chloride into nitrogen dioxide and molecular chlorine. In the first elementary process of the reaction mechanism, one molecule of nitrile chloride loses its chlorine atom, forming nitrogen dioxide and a chlorine atom. In the second elementary process, the chlorine atom reacts with another nitrile chloride molecule, forming nitrogen dioxide and molecular chlorine. The chlorine atom is an intermediate in this reaction. The chlorine atom created in the first step of the decomposition of nitrile chloride cancels the chlorine atom on the reactant side of the second step. The presence of an uncombined chlorine atom might be somewhat surprising to you, since you may have learned that chlorine is found as a diatomic molecule, not as a free atom. The chlorine atom is an intermediate in this reaction mechanism and exists for a very short period of time, since it is an extremely reactive form of the element. As you learned in the previous scene, the overall balanced equation of the decomposition of nitrile chloride does not reflect what is happening at the molecular level during the reaction. At the molecular level, it is not the collision of two nitrile chloride molecules that causes the reaction, which it might seem from the overall equation, but it is a series of steps that starts when a nitrile chloride molecule loses its chlorine atom. In contrast to the overall equation, each elementary process in a reaction mechanism is an attempt to reflect what happens at the molecular level. Since an elementary process portrays what happens at the molecular level, a rate law can be written using the coefficient of each reactant as the exponent. An example of how this is done is shown at the bottom of your screen. It is important to note that this is in contrast to the balanced equation for the overall reaction, for which the rate law can only be determined by experiment. In the reaction mechanism for the decomposition of nitrile chloride, discussed in previous scenes, there are two elementary processes. A separate rate law can be written for each one based on the coefficients of the reactants. This is in contrast to the overall balanced equation. Remember, if you are given the balanced equation for a reaction, you have no way of determining the rate law without experimental data. For the elementary processes in a reaction mechanism, however, rate laws can be derived using the coefficients. The rate law for the first elementary process is rate equals K1 times the concentration of nitrile chloride raised to its coefficient, which is 1. For the second elementary process, the rate law is equal to K2 times the concentration of nitrile chloride times the concentration of chlorine atoms, each raised to the power of its coefficient, in each case 1. In these equations, K1 and K2 are the rate constants for each elementary process. Again, remember that you can only derive rate laws for elementary processes, not the balanced equation. In most reaction mechanisms, there is one elementary process that takes place at a far slower rate than the others. Since the reaction cannot proceed any faster than the slowest step, this is known as the rate-determining or rate-limiting step. The rate-determining step can be compared to a slow ticket taker at a theater. People can arrive at the door at any rate, but they can only get through the door at the rate that the employee takes their tickets. The fact that the slowest step determines the rate of the reaction means that the rate law for the slowest elementary process is the rate law for the overall reaction. In the first step of the reaction mechanism for the decomposition of nitrile chloride, a chlorine atom splits off of a nitrile chloride molecule. The first elementary process has been determined to be very slow compared to the second one, which involves the highly reactive chlorine atom. This means that the first step is rate determining. This means that the rate law for the overall reaction will be the same as the rate law for the first elementary process, which is K times the concentration of nitrile chloride. Notice that this is the same result that was found experimentally in an earlier scene. When evaluating the plausibility of a proposed reaction mechanism, there are three crucial factors to consider, two of which have already been discussed. The first factor is that when the elementary processes of the reaction mechanism are added, the intermediates cancel, and the result is the overall balanced equation. The second factor to consider is that the rate law derived from the rate-limiting step is consistent with the experimentally determined rate law for the reaction. The third factor is that no elementary process involves more than 3 reactant molecules. In fact, elementary processes with more than 2 reactant molecules are relatively rare, and chemists never propose an elementary process with more than 3 reactant molecules. This is because it is extremely unlikely that more than 2 and at most 3 molecules will collide at the same instant with enough kinetic energy and at the correct orientation to react. Using the guidelines given in the last scene, you can evaluate a proposed reaction mechanism. Consider the combination reaction of nitrogen dioxide and fluorine gases, which produces nitrile fluoride gas. Experiments have shown that the rate law for this reaction is K times the concentration of nitrogen dioxide times the concentration of fluorine. Now, examine a proposed reaction mechanism. In the first step, 1 molecule of nitrogen dioxide and 1 molecule of fluorine collide and produce 1 molecule of nitrile fluoride and a fluorine atom. In the second step, the fluorine atom reacts with a molecule of nitrogen dioxide, producing a second nitrile fluoride molecule. Do the elementary processes add up to the balanced equation? As you can see, when the two steps are added, the intermediate fluorine atoms cancel, and the result is the balanced equation. In this reaction mechanism, the rate of the first elementary process has been determined to be slow, while the second is much faster. Which is the rate-determining step? Since the first elementary process is the slowest, it is the rate-determining step, and the reactants of that step are used to determine the rate law. The rate law derived from this step is K times the concentration of nitrogen dioxide times the concentration of fluorine. This is the same as the rate law that was determined experimentally. Since the elementary processes add up to the balanced equation, the rate law for the rate-determining step is the same as the experimental rate law, and no elementary step contains more than 3 reactant molecules. This is a plausible reaction mechanism. Think back to the reaction discussed at the beginning of the program, in which toxic carbon monoxide gas from a car's exhaust reacts with oxygen in the air, producing carbon dioxide. Even though essentially all of the carbon monoxide will eventually be converted to carbon dioxide, the reaction takes place very slowly at normal temperatures. By applying what you have learned in this program, you can understand why this reaction takes place so slowly. One reason this is such a slow reaction is the relatively low concentrations of the reactants. At standard temperature and pressure, the concentration of molecular oxygen in the air is 9.0 times 10 to the negative third moles per liter. If the concentration of carbon monoxide emitted from a car in a garage builds up to only 5.0 times 10 to the negative fifth moles per liter, it can be lethal. You know from collision theory that at lower concentrations of reactants there are fewer collisions, which lead to fewer reactions per second, and thus a slow reaction rate. In addition, the activation energy for this reaction has been experimentally determined to be high. As you know from collision theory, few molecules at room temperature have sufficient energy to overcome a large activation energy barrier. Now you can understand why the reaction of carbon monoxide and oxygen is so slow in the garage, even though the products are favored energetically. You have also learned enough to understand why catalytic converters are used on cars. The platinum and palladium in a catalytic converter increase the rate of the reaction by lowering the reaction's activation energy. This means that more molecules have sufficient energy to react at a given temperature. The metals in a catalytic converter are finely divided, which increases the surface area and therefore the reaction rate. You can see why carbon monoxide emission from motor vehicles is a potential problem, which has been addressed by use of catalytic converters. This program has introduced you to reaction rates. You have learned the concept of rate and specifically how rates of chemical reactions are determined. You saw that some reactions, like the combining of oxygen and hydrogen, happen almost instantaneously, while other reactions, such as the combination of carbon monoxide and oxygen, take considerably longer. You also learn the effects factors such as concentration, temperature, and surface area have on reaction rate. Collision theory and reaction mechanisms allow you to picture at the particle level what is occurring during a reaction and how this affects the rate of the reaction. Rate law expressions allow mathematical calculations of rate and relate to reaction mechanisms. Understanding reaction rates provides both practical and theoretical information to chemists. On the practical side, understanding the factors influencing rate allows chemists to manipulate the rates of important industrial reactions. On the theoretical side, understanding rate laws allows chemists to derive reaction mechanisms, which allows them to understand what is happening on the molecular level.